Hi everyone, welcome back to my videos. I'd like to do a video on a problem supplement uh, with challenging problems on tangents and secants. So let's go ahead to the first problem. So given that ABCD is a quadrilateral, a circle is inscribed in ABCD and the tangent points are R, S, U, and T. We want to prove that length of AB plus length of CD equals length of AC plus length of BD. So write down what we know, and I'm going to apply the betweenness property segments to get length of segment AB is equal to length of segment AR plus length of segment RB. Length of segment CD is equal to length of segment CT plus length of segment TD, and then do the same thing for AC and BC. So we can add what we have in statement 3 and statement 4 to get length of segment AB plus length of segment CD is equal to, length of segment AR plus length of segment RB plus length of segment CT plus length of segment TD. And we can also add what we have in statement 5 and statement 6 to get this quantity here. So I'm going to apply the two tangents theorem. So segment AS is congruent to segment AR. Therefore, the length of segment AS is equal to length of segment AR by the definition of segment congruence. Apply the two tangents theorem again. We get segment BU is congruent to segment BR. Therefore, the length of segment BU is equal to the length of segment RB. So I turned it around, and I did that because I set it up in 7 and 8. So you have to, this will make it a little bit easier when we do the substitution later on. It doesn't really matter for segment congruence. So segment CS is congruent to segment CT by the two tangents theorem. So length of segment SC is equal to length of segment CT. And then two tangents theorem one more time. Segment UD is congruent to segment TD. Therefore, the length of segment UD is equal to length of segment TD by the definition of segment congruence. So now I'm going to substitute what I have in 10, 12, 14, and 16 into 8. So what is, so AC plus BD is equal to, well, what's AS equal to? AS is equal to AR, right? So that's what we get here. What is SC equal to? SC is equal to CT. BU is equal to RB, and UD is equal to TD. So if I look at this quantity here and I look at the quantity I have in 7, the terms are kind of moved around, but it's the same quantity. So in other words, AB plus CD equals AC plus BD. Okay, so problem 2. So we're given right triangle ACB with right angle C. We're given a circle of center O and radius of length 3. We're given that the length of segment AB is equal to 15, and W, X, and Y are tangent points. Find the perimeter of triangle ACB. So we're done what we're given, and we can write that length of segment AB is equal to length of segment AW plus length of segment WB. Length of segment CB is equal to length of segment CY plus length of segment YB. Length of segment AC is equal to length of segment AX plus length of segment XC. All this is following from the betweenness property of segments, right? We know that AB is equal to 15, so I can substitute that into 5 to get length of AW plus length of WB equals 15. For this problem, for step 9, we're just going to accept that XOCY, this thing is a square, and opposite sides are congruent in a square, and therefore they measure the same thing. I'm actually not going to prove this because that would just add a lot of steps to this problem, and I think it's already long enough as it is. So we'll just accept that CY is equal to 3 and XC is equal to 3, right? Because OY and OX are both equal to 3 because they're both radii. Okay, we can apply the two tangents theorem to get segment YB is congruent to segment WB. Therefore, length of segment YB equals length of segment WB. By segment congruence, we can also apply two tangents theorem to get segment AW is congruent to segment AX. and therefore length of AW is equal to length of AX by the definition of segment congruence. Now, since we have a right triangle ACB, I'm going to use the Pythagorean theorem to get AB squared equals AC squared plus CB squared. I'm going to substitute, so we know that AC is equal to AX plus XC, and we know that CB is equal to CY plus YB. I plug those values into what I have in 14, and we get statement 15. I substitute what I have in statement 9 into statement 15, we get this. And then I use the fact that in statement 8, WB is equal to 15 minus AW. Plug that into 16 and then simplify, we get this equation here. If I solve for AW, I get AW is equal to 6 or AW is equal to 9. I didn't actually write the steps to solve this equation, but we'll just accept, this is the answer. I mean, if I have to write more steps, then, I think 24, 25 steps is already a lot, so I don't want to confuse you too much. But anyway, that's the answer. So usually you have to test both of these answers out to see if if one of them is extraneous, because one of them might not make sense physically, given the parameters of the problem. In this case, both these choices work. And so if I let AW equal to 6, then I get AX is equal to 6, WB is equal to 9, and YB is equal to 9. And you can just substitute into these steps here to get this conclusion. And therefore, AB is equal to AW plus WB. So you get 6 plus 9 was at 15. So AB is equal to 15. CB is equal to CY plus YB. So CY is 3, and then YB is 9, so we get 12. And then AC is equal to AX, which is going to be 6 in this case, and then plus XC, which is 3. So 6 plus 3 is 9, so AC is equal to 9. So the perimeter of triangle ACB is going to be 15 plus 12 plus 9, which is 36. If I use AW is equal to 9, you figure this out in exactly the same way, and you still get the perimeter of triangle ACB is equal to 36. So either way, the perimeter of triangle ACB is 36. Okay, given a circle of center B and a circle of center C, we're given that length of segment BT equals 5 and length of segment TC is equal to 9, and DET are tangent points. Find the length of segment AD. So I write down what I know, and then I'm going to draw radius BD and radius CE, because we can draw a line, and hence a segment between 2 points. We know radius is perpendicular to a tangent segment at the point of tangency, so segment BD is perpendicular to segment AD, right, because AD is a tangent segment. Segment CE is perpendicular to segment AE for the same reason. So we know that angle ADB, this angle here, and angle AEC are right angles, and therefore all right angles are congruent. Angle A is congruent to itself, so we can apply the angle-angle theorem for similar triangles to get triangle ADB is similar to triangle AEC. And we know that lengths in similar triangle measures of corresponding sides are proportional. So we get BD divided by CE equals AB divided by AC. So I I just wrote it the other way, but DB divided by EC, you can write it like that in this way. I just flipped it around. Doesn't really matter. When we're dealing with lengths, when we're measuring lengths, it doesn't matter which direction we take it, so you can just leave it like this if you want, or whichever way you prefer. So by the betweenus property of segments, length of segment AC is equal to length of segment AB plus length of segment BC. We know that segment BD is congruent to segment BT, right? Because they're both radii of this circle of center B, and all radii of the same circle are congruent. So BD equals BT equals 5, right? And we know BT is equal to 5, so we just apply segment congruence and, we substitute. Similarly, segment CE is congruent to segment TC because they're both radii, right? They connect points on the circle with the center of the circle. And then so length of segment CE is equal to length of segment TC is equal to 9. Okay, so what is BC equal to? Well, length of BC is equal to length of BT plus length of TC. So so if we add these two quantities together, we get 14. So length of BC is equal to 14. So once I plug all this stuff back in, what we have in 16, 18, 19, and into 13, we get 5 divided by 9 equals AB divided by AB plus 14, right? And I should actually include 14 in that step as well, but I didn't include it. So, because you just do AC, right? That's what we have originally in 13. So, sorry about that. But if we solve for AB, we get AB is equal to 17.5. Okay, now we can use the Pythagorean theorem and right triangle ADB. So AD squared plus BD squared equals AB squared, and then AD is equal to, you substitute, the values we have. AB is equal to 17.5, and BD is equal to 5, and then we get square root of 281.25, which is about equal to 16.77. So that's the length of segment AD. Okay, I'm going to solve one more problem, and I think we'll call it a night here, because these are all tough problems, so they're pretty demanding. So let's go over this. A circle of center O and radius of length equal to 5. The distance from the length of segment RO is equal to 13, and A, B, and C are all tangent points, and we want to find the perimeter of triangle RST. So we write down what we know. I'm going to draw radius OA and radius OC, because between 2 points a line and hence a segment can be drawn. And we know that segment RA is going to be perpendicular to segment OA, right? Because the radius is perpendicular to the tangent segment at the common point, right? The point of tangency. So, okay, we know that the radius measures 5, and we know OA is a radius, right? So length of OA is equal to 5, and then I can use the Pythagorean theorem. RA squared plus AO squared equals RO squared, and we can do that because RA is perpendicular to segment RA is perpendicular to segment OA, right? So this is a right angle, and hence this is a triangle. RAO is a right triangle. So we use the Pythagorean theorem, and then we can substitute, and we have, the values we have in 2 and 6, and plug that into 7. We get RA. Length of RA is equal to 12. So we know by the two tangents theorem that segment RA is congruent to segment RC. Therefore, the length of RA is equal to length of RC, and we already showed that RA is equal to 12, so RC is also equal to 12. Okay, segment SA and segment SB are also congruent by the two tangents theorem, so the length of segment SA is equal to length of segment SB. Once again, by the two tangents theorem, segment TB is congruent to segment TC, therefore the length of segment TB is equal to the length of segment TC. Now I can use the betweenness property of segments to get RA is equal to RS plus SA, right? And RC is equal to RT plus TC. So RS, what is RS equal to? RS is equal to RA minus SA. And we know RA is equal to 12 by 8, right? So RS is equal to 12 minus length of segment SA. RT is equal to RC minus TC, and we know that RC is equal to 12, so length of segment RT is equal to 12 minus the length of segment TC. Finally, I'm going to use the betweenness property of segments to get length of segment ST is equal to length of segment SB plus length of segment BT. But we know length of segment SB is equal to length of segment SA, right, by the reasoning with the two tangents theorem. And we also know that TB, length of segment TB, is equal to length of segment TC, again by the two tangents theorem. So I substitute, and then perimeter of triangle RST is equal to length of side RS plus length of side ST plus length of side RT. Well, we know we can just substitute what we found. So RS is equal to 12 minus SA, right? ST we found is equal to SA plus TC, and RT is equal to 12 minus TC. So if we add all these quantities together, the SA's cancel, the TC's cancel, and we just get 12 plus 12, which is equal to 24. So the perimeter of triangle RST is equal to 24. So that's all I have for you tonight. This was a pretty demanding video, but hopefully you get a little bit of exposure to some of the harder problems to get you to think. And we use just a common theme. We use two tangents theorem a lot, and we also use the betweenness property of segments a lot. So that will be helpful when you deal with tangents and segments and you're trying to solve some quantity. Also, the Pythagorean theorem is also useful. Alright guys, well have a good night, and I hope to see you during my next videos. Alright, take care.